Hello everyone, welcome to this lecture. I am Udom Philemon of Nubira Process Designer, and in this lecture I'll be introducing to you what the heterogeneous catalytic model is and how it works. Now I'll start with a brief explanation of this model. Now this model is used in cases where you have reactions that involve catalysts that are not in the same phase with the reactants involved in the process, right? So that's where this heterogeneous catalytic model comes in. Now this particular model takes this general form on my screen, that you have minus R is equal to kinetic term multiplied by potential term all over adsorption term. Now the minus R represents the rate, that's the rate of the reaction. Then you have the kinetic term, the potential term over the adsorption term. Now the adsorption term comes into play because the process involves a catalyst. So this adsorption term caters for the involvement of the catalyst in the reaction. That's why you have the adsorption term. So when you come in contact with a rate equation that has a division, then you have an expression beneath it. You have an expression at the top and then an expression below. Your likely guess should be that it is a heterogeneous catalytic model, right? So if you have a reaction that is taking this form, where the rate equation is taking this form, your most likely guess should be that it's the heterogeneous catalytic model, right? So now in this particular model we have three different kinds of models that were generated by different people. Now the first one, so we'll be considering this reaction where you have small a plus small bb is equal to small cp. Now based on this particular reaction, right, three models were generated by different people. Now the first one is the Langmuir-Hinshelwood model, which is actually the most popular heterogeneous catalytic model in use today, right? So you have the Langmuir-Hinshelwood, then you have the Allais-Riedel model, and then you have the Mans-Van Crevelen model. So like I said, the Langmuir-Hinshelwood model is actually the most popular heterogeneous catalytic model that is in use at the moment. Now if you are using Aspen Hysys to model heterogeneous catalysis, you would see heterogeneous catalytic while choosing your reaction model. But if you are using Aspen Plus, you may not see heterogeneous catalytic. What you will be seeing is Langmuir-Hinshelwood Hogan-Watson, right? So either you see Langmuir-Hinshelwood or you see the heterogeneous catalytic. Now each of these models have their individual rate expressions that you can see on my screen. So you have the expression for the Langmuir-Hinshelwood, then you have the expression for Allais-Riedel model, then you have the expression for the Mans-Van Crevelen model. So now mostly we'll be working with this first one, which is the Langmuir-Hinshelwood model, right? It is widely used in modeling a lot of heterogeneous catalytic models. So we'll be using most of it as our example in this tutorial. Now let's move over to some examples of heterogeneous catalytic models so that I can explain further. So going back to the rate expression, the general expression, we have minus R is equal to the kinetic term multiplied by the potential term all over the adsorption term. Now looking at the Langmuir-Hinshelwood, comparing it with this general formula that we have up here, you have the kinetic term, then you have the adsorption term, and then the potential term. So now the expression at the denominator is called the adsorption term, or some others call it the denominator term, right? Then from here we have our K plus in the numerator. The K plus is the reaction rate constant, right? Then the capital K that we have at the numerator is the adsorption rate constant for that particular component. So Ka is the adsorption rate constant of component A. Kb is the adsorption rate constant of component B. So this, for example, this Langmuir-Hinshelwood model actually takes the form of this general model, which is the kinetic term multiplied by potential term all over the adsorption term, right? So let's look at some examples of heterogeneous catalytic models. Now here we have a few expressions that can help us understand this model better. Now for the first one, we are considering certain hydrodesulfurization reactions. For the first reaction, you have RSH plus H2 to give you RH plus H2S. Then you have COS plus H2 to give you CO plus H2S. Now let's go back to this. Okay, let's go back to our example. Now one thing you must notice in this heterogeneous catalytic model is that it has both it can be expressed via both forward and backward reactions, right? The numerator term can have both forward and backward reactions. Now when the reaction involved does not have a backward reaction, then the Kr for the reaction will be 0, right? So for example, now in our first two examples, we have just forward reactions. If you can see the arrows of the reaction, they are just forward. So this rate expression is expressed only in terms of the forward reaction, right? So this is based on just the forward reaction. There is no backward reaction here. So in this case, you just have your kinetic parameter, your driving force, right? Yes, that is your driving force or your potential term, then all over your adsorption term, which is this that we have below. Now this adsorption term, right? This adsorption term, if we are going to work with it, it would have to be expanded. It will have to be expanded. So by the time you do the expansion calculation, you get your denominator term or your adsorption term to be equal to this right here. Now I'll be using this to illustrate how values from this equation should be inputted in Aspen Hysys. So we'll go to our Aspen Hysys environment. Now I already chose the heterogeneous catalytic model. We can click on it. Okay, let's go back. Let me open a new case quickly. Coming up. Okay, so let me quickly do this. Okay, so I'll just quickly go into the reaction section because that is where I want to illustrate. Okay, so you click, if you want to use the heterogeneous catalytic, you click on it and then you click add reaction. Now this is what I wanted to show you right here. So now from the kinetics help, you have this, you have for the numerator, you have K times F basis minus K prime times F basis. Now this K prime that is here represents the reverse reaction, the kinetics of the reverse reaction. So when you are dealing with an irreversible reaction, K prime will be equal to 0. Right? That's what I said earlier. Now let's go back. So what we have here, for example, for this first equation, what we have in this rate equation is what is supposed to be inputted, right here. So I'll be using this first example to explain how to input and specify values here. Now you have your numerator, then you have your denominator, which has been simplified into this. Now the values for K can be gotten here from this table right here. Now let's go back. Now from this particular form we have here, we have the base units and then we have the rate units. Now for the rate units, Aspen Hysys can only be used for rate units that is based on reactor volume, right? We mostly have like two types of rate units in this heterogeneous catalytic. So we have the rate unit that is based on reactor volume, and then we have rate unit that is based on catalyst weight. So before you start modeling a process using Aspen Hysys for heterogeneous catalysis, you must check the rate expression and be sure that it is in meter cube, right? You must ensure that the rate expression is in meter cube. So if you go back to that form, now we have RSH is equal to this. Now if you check the table, we have this table right here. We have this KO to be with respect to G cat. Now this G cat signifies that the rate basis is based on catalyst weight, right? So this particular model should not even be simulated with Aspen Hysys, right? It shouldn't, because the rate expression, now this K is dependent on the rate expression, right? It's dependent on the rate of the reaction. The unit of K is dependent on the rate of the reaction, the rate unit, right? So for it to have G cat means that the rate unit also is in G cat, and which means that this particular rate equation that we have here is based on catalyst weight. And it also means that it should not be simulated with Aspen Hysys, because from what we have here, all of them are either in meter cube, liter, centimeter cube, milliliter, or feet cube, which means all the rate units we have in Aspen Hysys is based on reactor volume, right? So that's one of the things you want to check when you are simulating your heterogeneous catalytic model, right? So you must use rate equations that are based on reactor volume if you are to use Aspen Hysys. Now let's go back to the reaction rate. Now you have the numerator section, which consists of the forward and the backward. Then you have the denominator section. Now going back to our problem, now our formula is RSH is equal to K into this over all of this. Now K is equal to K naught exponential minus E over RT. Now from this table we have K0, which is K naught, right? And we also have activation energy, which is E. So simply put, we can extract both our K values and our activation energy from this table for each of the equations. That's for each of the mercaptan compounds, right? So this equation we have here is like a general equation which requires you to input the specific compound you are working with, right? So if we are working with methyl mercaptan, for example, we are going to be using these first two values for our value of K. Now these two values will be inputted, that is 4.74 times 10 raised to power 5 and 25 kg per mole will be inputted here. They will be inputted here in the forward reaction for A and E, right? So for A it will be 4.47 times 10 raised to power 5, and then for E it will be 25 kg per mole, right? That is what we'll put. Now for the reverse reaction, we are not going to input any values for it, right? We are not going to be inputting any values for it because this particular process does not have a reverse reaction. Now going back to the stoichiometry aspect, we also have the basis units, right? The basis units. Now let's go back to that equation. Now in that equation, the rate expression, we have K multiplied by PRSH times P 0.5H2, right? That is the numerator term. Now to know the basis units, right, the basis unit, to be able to determine it, you have to look at the particular parameter that is beside your components, right? So beside our components in the numerator we have P. Now what that P signifies is partial pressure, right? So it signifies partial pressure. So normally you should go back to your stoichiometry form and change the basis units. Is it from here? Okay, you change it from here, basis, you change it to partial pressure, right? You change it to partial pressure, and why we are changing it is because that is the parameter that was used in this particular rate expression, right? So you can have others too. From what we saw, you can have others. You have activity, molar concentration, mass concentration, mole fraction, mass fraction, and fugacity. So depending on what you have in that particular rate expression will determine which of them you will choose. But in this case, we get to choose partial pressure. And why we are choosing partial pressure is because that is what is present in this particular rate expression, right? So you choose partial pressure. Then let's check the table again. Okay, so from the table we have KO has mole over kPa, right? So our exact unit for pressure will be kPa, right? So we don't need to change this. We change to partial pressure because of the rate expression, but we don't need to change this one, right? Because our K naught value is with respect to kPa, right? So sometimes it may be pressure, some other times it can be ATM, any of the different units of pressure. So you have to also look out for that as well, because all these things will affect your eventual results while simulating this particular model. So you have to be very careful with all this. So that's for both the basis unit and the rate unit. Now we go back to the reaction rate. So I have told you what to specify here, right, for A and E. Now you have the components. Now the components, for the components, you would specify the components of each of the numerator terms. Now let's go back to that. So we have PRSH times PH2 raised to power 0.5. Now in the numerator term we have RSH, right, and we have hydrogen. Now we'll be specifying both of them in that numerator section, and we'll be specifying the exponent that is associated with each of them. Now let's go back there. So for these components, for example, if we added hydrogen to our component list, we'll specify hydrogen here, and in the forward order we'll specify, let's check. So for hydrogen, the exponent is 0.5, right? So we'll be specifying 0.5 in this forward order. Then we'll also choose the RSH that we are using for that particular equation and we'll specify 1, because P RSH is also P RSH raised to power 1, right? So that is how we are going to specify the numerator aspect of this particular model. Now for the denominator, we have resolved this particular brackets, these two brackets, we have resolved it into this, right? So this is what we will actually be specifying in the denominator. Now if you check this denominator, it is supposed to take this form. Still, it is supposed to take this form of K is equal to K naught exponential minus E over RT. More like it is supposed to take the form of the Arrhenius equation, right? So let's go back to the form. Yes, it is supposed to take the form of the Arrhenius equation. Now you would also specify it in a way that will be similar to the numerator, how the numerator was specified, right? So you'll be starting with each of the terms and be specifying them similar to how the numerator was specified, right? So if you take the first term, which is 1, you input it in, you input it here, right? Then you specify both the A and E values. Then you specify the exponent of that particular component that is associated with that term. Now let me go back and explain better. Now you have 1, the next term is 0.00468 pH2. Now in this 0.00486 pH2, right, if you model it to look like this, which is K is equal to K0 exponential minus E over RT, you would notice that this particular expression just has a value for the pre-exponential factor, right? It doesn't have any value for activation energy, right? So in this case, activation energy will be 0 for this particular term, right? Because it just stops at the first value, which is K, right? There is no E raised to power something something something, right? So you'll be specifying only the A value for this particular term, right? Then you will now specify the component, which is hydrogen, and then you specify the power of the parameter, which is pressure, and in this case you have P, and that P will be equal to P raised to power 1, right? So by the time you add the component, which is hydrogen, you will be specifying that hydrogen is 1, right? So now where you will understand this better is when I simulate the first example, right? I'll be able to explain this particular concept better to you, which is what we are going into now. I just wanted to try and explain it briefly before we now go in depth into it. Now, the last thing you have here is the denominator exponent. Now, the denominator exponent is just the exponent of the denominator, which in this case, if you check, now initially we had the first bracket is raised to power 1 and the second bracket is raised to power 2. But after expanding, you will have that the whole denominator exponent is raised to power 1 after the expansion of this. So the denominator exponent is the exponent of the denominator. So you have to look out for that and look out for it very carefully. Okay, now we'll be using this to explain how this heterogeneous catalytic model works quite better. So after seeing this particular example, you should be able to understand what I was saying previously better. Now, in this case too, it's also a forward reaction from the reaction equation. You see, it's a forward reaction, and that is why you have 0. You have 0 right here because it is a forward reaction. If it was a reversible reaction, you would still have a particular expression by the side here after the minus sign, right? And yes, this one can be simulated in Aspen Hysys because your rate is in terms of kilomole per meter cube. So that meter cube is what is important here, which signifies that this rate expression is based on reactor volume, right? So, and reactor volume can be simulated in Aspen Hysys, right? So that is why I chose this example for this particular tutorial. Now, you have your rate expression, you have your numerator and your denominator, right? Now, you see that this is quite different from the first one. The first one, we had P in our numerator and denominator terms. We had P, which signified partial pressure, but in this case, what we have is C. As you can see, is C that we have both in the numerator and in the denominator, right? So this C now represents the molar concentration of the components involved, right? So in this case, our basis unit wouldn't be partial pressure. Instead, it will be molar concentration, right? So you have to look out for all these things while you are trying to use this model in order to use it effectively. So let's go to the simulation environment. This is the particular one we'll be simulating now. Already, okay, let's see. So first off, you have to specify your components: chloroform, H2O, oxygen, CO2 and HCl. Then our fluid package is pengrobinsin. So you specify your fluid package and your components before you start to specify your reaction. So in reactions, you click add and it creates a reaction set for you. You open it and you click on add reaction. You click on add reaction. It will ask you if you want which of the models you want to choose. You click on heterogeneous catalytic and then you click add. Then you exit this, right? Then in order to specify it, you click on it, reaction 1, and then you can begin your specification. Now you specify your stoichiometry and ensure that you have a balance error of 0, right? Based on the equation is already balanced from here, so you just use that to balance your equation. For reactants you have negative, and then for products you have positive, right? Now your basis is automatically on molar concentration, and in this case it's correct because we have C in our numerator and denominator terms, right? So, and that C signifies molar concentration. So we can go back and continue our specification. Then base components, I would use chloroform I'll use chloroform as the base component. Then reaction phase is vapor phase. Reaction phase is vapor phase. Then chloroform is the base component. Then for base units, what are we using for base units? Okay, we'll leave it at kgmol per meter cube, right? Then for rate units, let me confirm that one. Okay, yes, it's kgmol per meter cube second, right? So we have fully specified this section. So the next section is the reaction rate, which will be specifying singly until we are done, right? So this was already inputted by Hysys because I already specified the stoichiometry. We may have to modify some of the numbers here before we continue. So now it is a forward reaction in this case, so we are not going to be dealing with the reverse tab, just the forward tab. So let's go back to the expression and get the numerator values. So from here, for the numerator, we have 3.72 times 10 raised to power 5. This is our K value, which in Hysys will be our A value, right? So this is what we'll be putting it as A, right? Then for let me zoom into this. For our activation energy, we'll be making use of this value right here. So let's input it. Just pick out the numbers. So we have 3.72 times 10 raised to power 5. That is 3.72 E5. Let me confirm that. 3.72 E5. Okay, then this one is 21,700. Let me check. 21,700, yes. So that is that for the A and E value. Then what do we have next? We now have to put our exponent. So for the molarity, the molar concentration, all we have is CH3Cl, right? CH3Cl, and the power is 1, right? Because we have CH3Cl, which is also C raised to power 1 CH3Cl, right? So the power there will be 1. So for chloroform, for forward order, we would have 1 here. We would have 1, and then we would have 0 for the rest, right? Because we don't have values for them, and that is because they are not part of that particular concentration. So they will all be 0, right? They would all be 0 because what we have there is just CH3Cl, right? So it will be 0 for the rest and 1 for CH3Cl, right? So we have fully specified our numerator. Now let's go to the denominator. From here, our denominator exponent, the denominator exponent is 1, right? Because whatever is in this bracket is raised to power 1 automatically. So our denominator exponent is 1. So what we are left with is specifying the individual component exponents. Now let's go back again. So right here we have 1 plus all of this. Now for this one, the particular one we have here, it can actually be ignored because it is not with respect to any of the components, right? So there is no need inputting it. If you input it, you have to specify 0 for each of them because they are not attached to it, right? So we'll be specifying for just those ones where we have the molar concentration and then we have the components beside it. So for this one, we have HCl, and then for this one we have CHCl3, right? So we can start with this. Now you already have the value of the pre-exponential factor, then you have the activation energy value, so we'll be specifying that. Now for this first one, I can't do that. Let me see. We have 5.97 E3. 5.97 E3. Yes. Then we have the activation energy. That's 2440. 2440. Yes. Now we go and look at the compound that is attached to it. In this case, it is HCl, right? So HCl will be specified as 1, right? HCl will be specified as 1, and that's because the power of that concentration is 1. The power of that particular concentration term is 1, and that's why HCl will be specified as 1. Now you look for HCl. Okay, see HCl here. You specify it as 1, and then the rest will be 0. They will be 0 because they are not part of that particular term, right? So they will be 0. Now for the second one, you have CHCl3, and the power of that particular concentration is also 1, right? So let's specify the kinetic parameters. Now you have 1.23 E3. We can quickly specify that here. 1.23 E3. Enter. Then we have our activation energy. Activation energy is 5330. 5330. Okay, let's go back and confirm something. Okay, now in this case, our activation energy would be minus, right? We'll be inputting it as minus because it is positive right here, right? Normally you have K is equal to A e raised to power minus EA over RT, right? So you have minus EA is equal to this value, right? So you have minus EA is equal to 2440. EA will now be equal to minus 2440, right? Like in the case of the numerator, EA is equal to minus EA is equal to minus 21,700. Therefore EA will be equal to 21,700. But in this case, you have minus EA is equal to 2440. Therefore EA will be minus 2440, and EA will be minus 5330 for this other one. So let's make that adjustment before we continue. So here should be minus 2440. Minus 2440. Enter. Then here should be minus 5330. Enter. Then now we can specify the component exponent, which is 1 for CHCl3. So we just, okay, CHCl3 is already here, so we specify it. So the rest will be 0 as well, because they are not attached to that particular term. So each of them will be 0. So at this point, we are done specifying all parts of this particular model, the numerator, the denominator, and everything. We specified everything, and we are ready to simulate the process itself, right? So you exit this, and then you attach to fluid package like you would always do. Now when you attach to fluid package, if you check, Hysys then calculates the rate of reaction only after you have attached the fluid package. So we are good to go now. Now we can go to the simulation environment because everything is fully specified. Now in the simulation environment, we are going to be making use of a plug flow reactor, which can be found in the reactor section of the palette, right? So we're specifying our feed, and then our product. Our feed and our product, then we can attach our reaction set as set 1. It says unknown dimensions, but before we get to the dimensions, let's specify our feed. So from the problem statement, our feed is 100 kg mole. Then temperature is 100 degrees Celsius, pressure is 1 atm. Let's quickly do that. 1 atm, then 100 degrees Celsius. Okay, then our composition, and we are good. So for composition, you have 0.4, 0.4, 0.2, 0.4, mole fraction 0.4, 0.4 water and 0.2 oxygen, 0.4 water and 0.2 oxygen. Then this is okay. So we specify this. Okay, let me check. Okay, our feed is fully specified now. Then for parameters, we can specify our pressure drop as Ergon equation. We can use Ergon equation so that Hysys calculates the pressure drop. Then we can now go and specify the dimensions in the ratings tab. So for dimensions, you have a length of 2 meters and a diameter of 1.5 inch. So 2 meters, 2m, and then 1.5 inch. 1.5 inch. Yeah, so we are done specifying our reactor. In case your process requires an energy stream, you can add that and specify your outlet temperature, but that's not the case in this particular problem. So that's how to specify your reactor. Now you can check the product composition, right? You can check the product composition. So we produce CO2 and HCl from this process based on our kinetics. Let me scroll up a little. Yes, and this is what we have as our product composition, the effluent from the reactor, right? So this is how to specify the heterogeneous catalytic model in Aspen Hysys. At this point, we have come to the end of this particular tutorial. I hope you gained some knowledge, right? If you have further questions on this particular model, I would like to hear them from you. So just comment, use the comment section, then like this video and subscribe to this channel for more tutorials on process simulation. Thank you and have a good day.